Hello, it's Stat 135, Lecture 13. We're continuing our discussion about sufficiency. So let's remember what a minimal sufficient statistic is. So minimal sufficient statistic is when the partition under T is the same as the likelihood partition. You can see it in this example here, where x1 and x3 are Bernoulli. So the likelihood partition, it has 4 partitions, and the partitions, for example, of 3 also has the same partitions. So another characterization of minimal sufficiency is that if so equality under T of x1 to xn and y1 to yn is equivalent to the ratio of the likelihoods not depending on theta. So we'll see an example of that right now. But what we're going to do today is we'll talk more about sufficiency, minimal sufficiency, and Rao-Blackwell theorem, and then we'll start with hypothesis testing. So if you look at this example, x1 to xn IID Poisson, you can see that the sum of the xi's is sufficient because we can factor the likelihood into a part that depends on t and theta and a part that depends just on your data. And we can see that it's minimal sufficient because the ratio for this not to depend on theta, we can see that the sum of the xi would have to be equal to the sum of the yi. And so that would be if and only if t is a minimal sufficient statistic. So equivalence under x1 to xn and y1 to yn under t would be equivalent to this ratio not depending on theta. Furthermore, we can see that the sum of xi x1 is a sufficient statistic. We know that the sum of xi is sufficient, and just adding another component to that will just make a finer partition. And so being a finer partition means that it's still a sufficient statistic. You can see an example of this here. If you look at T4 compared to T3, T4 just has one more component, and it's a finer partition than T3, and hence a finer partition than the likelihood partition, hence it's sufficient. Furthermore, some of these xi x1 can't be minimal sufficient because, again, it's finer than sum of xi, which is minimal. So to summarize, by the factorization theorem, we can see that finding theta that optimizes or likelihood is equivalent to finding theta that optimizes this function g that's dependent just on your sufficient statistic and theta. So there are many sufficient partitions of the outcome space from the entire outcome space, x1 to xn, which is the finest or maximal partition, to the MSS partition, which is the coarsest or minimal partition. So the Rao-Blackwell theorem is a real motivator for why we should care about sufficient statistics, because it says that through the Rao-Blackwellization process, we can get an estimator that's going to have a lower MSE, unless that the estimator is already a maximum likelihood estimator. So the statement is you have an estimator of theta. Its expectation of the of theta hat squared is finite. Suppose t is sufficient statistic for theta, then the conditional expectation of your estimator condition on t is a new estimator that will have a smaller MSE, and equality only holds when your original estimator is a function of t, as it is when theta hat is MSE. So let's just look at an example. So x1, xn, IID Bernoulli, we're going to let t be the sum of the xi's, which is a sufficient statistic. We'll let theta hat be x1, which is not an MLE estimator. We're going to Rao-Blackwellize this by looking at the conditional expectation of theta hat conditioned on t. And we use a trick here. The x1, xn are identically distributed, so the conditional expectation is just n times the conditional expectation of x1. And since x1 to xn is x1 plus x2 up to xn is t, the expectation, the conditional expectation of that will just be t, because we're conditioning that t is little t. So what that tells us is that theta twiddle is just t over n, which is the sample mean. So we have now a new estimator, which by lecture 11 we know it has a smaller MSE than the MSE than the estimator that we started with. So it's worthwhile looking and understanding the proof of the Rao-Blackwell theorem. So since t is sufficient, theta hat condition on t doesn't depend on theta, and hence it's a statistic. And furthermore, theta twiddle, which is the conditional expectation of theta hat condition on t, it's a function of t, and by the property of iterated expectations, it'll have the same expectation as theta. It'll have the same expectation as theta hat. So theta twiddle and theta hat have the same bias, and hence, since MSE is bias squared plus variance, we're going to show that the variance of theta twiddle is smaller than the variance of theta hat. So the variance of theta hat, we can have an expression for this using our formula for iterated variance. So this expression is in Pitman, and I think it's chapter 5 or 6, and so it's basically the relationship between conditional expectation and conditional variance. And so what we can see is that the expectation of the variance of theta hat conditioned on t is greater than or equal to 0, because the conditional variance is obviously greater than or equal to 0. So we're going to have a strict inequality exactly when theta hat is not a function of t, because when theta hat is a function of t, then the variance will be 0, and so the expectation would be 0. So what we see from this is that the variance of theta hat is greater than or equal to the variance of theta twiddle. And so the MSE of theta hat is greater than the MSE of theta twiddle with equality only when theta hat is a function of t. So that finishes chapter 8. Congratulations. And now chapter 9, we're just going to briefly start on hypothesis testing. We're going to concentrate on the frequentist approach. So a hypothesis is a statement about a population parameter. We're going to have two competing hypotheses, the null and alternative hypothesis. A decision function will decide between these two. So we define we say that dx is 1 if we reject the null, and dx is 0 if we accept the null. And there are two errors that you can have. You can have a type 1 error, which is when you when you reject the null when in fact the null is true. So that p sub 0 means that we assume the null distribution is correct. So this is called a false positive. The other type of error is called a false negative, and that's when the other possibility is you would accept the null when actually the alternative is true, right? So examples are that a company claims they have a screening test for breast cancer that detects with a frequency of 0.7. The null is 0.5, the alternative is 0.7. You collect a sample that supports that the screening test works, but it really doesn't work. And a false negative would be where you collect, where your sample supports that the screening test doesn't work, but it really does work. So many think that a type 1 error is worse than a type 2 error. And so because, as we'll see later in the course, alpha and beta are negatively correlated, so you can't lower both arbitrarily in your experimental design. So what we do is we fix alpha to be some acceptable, tolerable level, which is 0.05 or smaller generally, and then we try and design an experiment that'll minimize your beta. And so alpha is called the significance level of the test, and we will pick up all of this stuff on Monday. Have a great weekend.